In the previous lesson, we had some insights into the heat capacity of molecules in the gas and learned about the connection between this heat capacity and the kinetic energy of these systems, which are proportional to the number of degrees of freedom. And we distinguished monatomic molecules from linear molecules and nonlinear polyatomic molecules. Now we will expand this to the heat capacity of large molecules such as proteins, and we will see that there's an additional influence of potential energies and of vibrations. Particularly, we will learn why we ignored vibrations for small gas molecules previously. Potential energies we could ignore because it was an ideal gas that we studied. It doesn't have a potential energy, but we ignored vibrations. In order to understand why we ignored vibrations for small gas molecules, we need some brief insights into quantum mechanics. And we will learn how to measure heat capacities experimentally using a technique that is called differential scanning calorimetry, or DSC. And this allows us, for example, to measure the heat that is required to unfold a protein. Now first, let's see how we can translate some of our concepts that we learned for an ideal gas to a protein and how far we get with that. Let us assume a small to medium-sized protein that has 2,000 atoms. That's not a very large protein, but that's a reasonable number. It is simply an example. So let us assume the first approach, in which we consider that every atom of a protein contributes 3 degrees of freedom. So in this case, we basically allow each of these atoms to move independently, similar to the atoms in a monatomic ideal gas. And for every protein, we basically have 2,000 atoms, and each of them corresponds to or contributes to 3 degrees of freedom. And that gives us per protein 3 times n, where n is the number of atoms, so 6,000 degrees of freedom. From each of these degrees of freedom, we have an average kinetic energy of 1/2 kT, which is something that we learned previously. And the average kinetic energy of a protein is 3n, so 6,000, times 1/2 kT, or 3,000 kBT. Now this is of course per molecule of protein. If we express that per mole, then we just replace the Boltzmann constant by the gas constant, and then we obtain 3,000 RT instead. Now this kinetic energy has a contribution to the heat capacity of a system. When we want to change the temperature, we need to change the kinetic energy, and this already tells us how much energy we need per Kelvin. This is simply the derivative of its kinetic energy with respect to temperature, and that is 3000 R. Now mind in this case that this is the contribution of just the kinetic energy to the heat capacity. Proteins are not an ideal gas, of course, so in addition to the kinetic energy, we also have a potential energy. When we're changing the temperature, that changes as well. So we also need to take into account the derivative of a potential energy with respect to the temperature and add it to the contribution from the kinetic energy. However, we do not have a simple description of that. So while we can write out the kinetic energy like this, we can simply take the derivative of that with respect to temperature. We don't have a corresponding simple description of the heat capacity contribution from the potential energy. So we just have to live with this kind of abstract description over here for now. Now a second approach. Why don't we just assume that our protein or large molecule is simply another example of a nonlinear polyatomic molecule, just like in the ideal gas, where we assume that there are only 6 degrees of freedom, 3 translations and 3 rotations. So instead of 3n degrees of freedom, instead of 6,000 degrees of freedom, we only consider 6. What we do in this case is that we are neglecting 3n minus 6 degrees of freedom. And these 3n minus 6 degrees of freedom are called vibrations. A protein, just like a nonlinear polyatomic molecule, can translate and rotate in 3 different directions, rotate around 3 different axes. And in addition, it can also vibrate. These are changes of the conformation of a protein, for example. Now, if you apply this to our protein example of 2,000 atoms, we would neglect 5,994 vibrations. That's a lot of vibrations, of course. Potential energy in ideal gas was always 0 and does not contribute to the internal energy, so this is what we used for a nonlinear polyatomic molecule. That, of course, is not true for a protein, but this is basically these 2 extreme cases. Here we are assuming that every atom of a protein can be basically treated independently and has 3 degrees of freedom. Here we're saying that we only have 3 translations and 3 rotations for the entire protein, and we ignore every vibration. Now the question, of course, is which approach is correct? And the answer to that, as you might suspect, is neither. So the correct answer, how to describe the heat capacity for a protein, is essentially somewhere in between these 2 extreme cases that we just discussed. Now, what parts of these 2 previous approaches are actually correct? What do we have to consider? Well, there are 6 so-called classical degrees of freedom, 3 translations and 3 rotations, each with an average kinetic energy of 1/2 kT for a protein. So these 6 degrees of freedom do exist. And of course, we have a potential energy that contributes to the internal energy. So the internal energy of a protein is the kinetic energy plus potential energy, and that is not zero, it's not an ideal gas. And as a constant consequence of that, this potential energy, of course, as we saw before, and now it's a little bit more formal, contributes to the heat capacity. Here I'm writing down the heat capacity for constant volume. So the change in internal energy with respect to the temperature, there's a contribution to the change of the kinetic energy with respect to temperature, and the change of the potential energy with respect to temperature. Here in all 3 cases at constant volume, but I can write down the same thing with constant pressure as well. Now, these 3n-6 vibrations that we neglected for the ideal gas case of a simple rigid polyatomic nonlinear molecule, these 3n-6 vibrations also contribute to the internal energy and the heat capacity. A quantitative description of that goes pretty much far beyond the scope of this course, but I will provide in the following slide a qualitative description of what is going on. So we cannot ignore those, obviously. We also saw that there are many of them, but they're actually not so easy to describe. The key problem with vibrations is the quantization of energy, which is a result from quantum mechanics that you might have heard about before. Essentially, we can separate 3 different scenarios for the vibrational degrees of freedom, and the problem is that we find all 3 of them in proteins. The first one, the thermal energy, is much larger than the separation between allowed energy levels. The separation between allowed energy levels is actually proportional to the frequency of vibrations in this potential. I'm using here an harmonic potential to illustrate this. So it's proportional to the frequency of vibrations in there. And if the thermal energy is larger, I'm illustrating this here with this gray bar, and the separation between these different states, then we are approaching basically a classical limit. So here things start to behave normal. You expect that we have an average kinetic energy, which is roughly 1/2 kT, as we saw previously for translations and rotations. And basically these degrees of freedom here, vibrations where this condition is fulfilled, essentially that means that the frequencies are very low and the thermal energy is larger than h, this is the Planck's constant times that frequency. In that case, this behaves essentially classically, and we can be almost treat it like a translation or a rotation. Now, the other extreme case is where the spacing between allowed energy levels is very large in comparison to the thermal energy kT. This is the case when we are essentially stuck in the ground state because we are exciting vibrations, we are basically pumping energy into the vibrations via collisions of molecules. The molecules are colliding with each other, and the amount of energy that they can transfer in this case is, well, at most something proportional to the thermal energy that is available in the system. Because this is the kinetic energy that the molecules on average have. This is basically what they can give to each other in order to excite vibrations. Well, if this is too small, it's not enough to go from the lowest vibrational level to the next one, then we are essentially stuck in this lowest vibrational level. And that does not change for any moderate change of T. So unless we change the temperature by multiple factors, essentially, so we go from 300 Kelvin maybe to several thousand Kelvin, then this picture doesn't change much. So we are stuck in this lowest energy state, and that does not change when we're changing the temperature. And that means that, well, there's no change in the energy when we change the temperature, and that means there's no contribution to the heat capacity. And anything that we learned about classical mechanics does not apply in this case. So thermal energy is much smaller than the energy spacing between allowed vibration levels, so h times the frequency, then things behave very differently. This is what we used previously for small molecules. This is why we we're allowed to ignore vibrational degrees of freedom in small rigid gas molecules, because essentially this is the case. The energy required to excite a vibration from the lowest energy level to the next energy level is so large that at room temperature this just doesn't happen. Now, in addition, we can have something in between. The thermal energy is similar to the energy spacing, and now we are essentially sitting somewhere in between. Classical mechanics doesn't completely apply. We won't expect an average kinetic energy in these vibrations of 1/2 kT. It's also not fully, well, it is quantum mechanical, of course, but it's not in the case where classical mechanics doesn't apply at all anymore. We are able thermally to excite these vibrations, but essentially we are somewhere in between. Now, as mentioned, the problem with proteins is that we find all these different types of vibrations. A protein doesn't have only a few vibrations, it has many, as we saw for our example, more than 5,000 vibrations, and some of them fall into this category, some of them fall into this category, some of them fall into that category, and taking all these into account is not trivial. Now, what we can take away from this is that the theoretical description of the heat capacity of proteins and other complex molecules is extremely hard. For this, we actually need very sophisticated computer simulations and a lot of statistical mechanics and statistical thermodynamics. This is something that you might, if you choose, learn about in other courses, more advanced courses in the future. However, the heat capacity of a protein is a real thing, and we can actually measure that in experiments. We can do it for proteins, we can also do it for other complex materials. This is even done while changing the temperature. So we're not only measuring the heat capacity for one particular temperature, but we scan through the temperature and basically measure how much heat we require in order to change the temperature, and that tells us something about the heat capacity and its temperature dependence. We can do that, of course, at constant pressure and at constant volume. So that depends on how we basically set up this experiment, if we keep the volume constant or if we allow the volume to change and instead we keep the pressure constant while we are heating the system. Now, the experiment of choice for this, as I mentioned at the very beginning, is differential scanning calorimetry, which we abbreviate as DSC. This is an example for a lysozyme protein in solution. So this is what that roughly looks like. A relatively large complex molecule. You see all the different atoms. You see it's a big mess, essentially. It's a big blob of many, many atoms. Understanding the detailed molecular structure of this is going to be a little bit more challenging. But anyways, we can put it in a solution and we can heat it. We can change the temperature. And while we're doing this, we are measuring how much heat is required to change the temperature. How much, usually it's an electrical current that is used to heat the solution, how much is needed to change the temperature. And we can see that this is not constant. You can see it's slowly increasing at low temperatures, and there's a bump over here, and then it becomes more or less not constant again, but becomes a linear change again with increasing temperature. You also can look at the units. We see here that it's reported in kilojoules per mole per Kelvin. So previously, when we talked about heat capacities, we usually found them to be in the order of joules per mole per Kelvin. Here we talk about kilojoules per mole, because proteins are very large molecules. We need a lot of heat to change the temperature. Now, as I mentioned, in the differential scanning calorimetry experiment, we use a protein solution and we heat it, and we measure the amount of energy that is needed to increase the temperature, and that is essentially just the heat capacity of a protein. If we measure the amount of energy required to increase the temperature by 1 Kelvin, that is the heat capacity, and we do it while we are changing the temperature. We can do it with a protein in solution, and then we can compare that to just the buffer without the protein. The difference tells us basically what the heat capacity of just the protein itself is. Now, a peculiar thing is this peak at around 78 degrees Celsius. So at some point the protein will unfold. It will transition between this folded structure, which is a native structure for protein, into something that looks very different and actually doesn't have a defined structure anymore, and the protein structure essentially falls apart. And this happens at this temperature, as we can see here in this peak of the heat capacity. Why is there a peak? The reason for that is when this transition happens, we are not only heating up the system, but we are also performing work. This work goes into breaking hydrogen bonds in the protein, essentially destroying protein structure. That requires work. Everything that holds the protein together you have to work against it in order to break it, and this is happening here, not at one particular temperature, but basically it starts at around 70 degrees Celsius, it peaks at 78 degrees Celsius, and we're still not completely done, and then at around 90 degrees Celsius, whole protein or all proteins will essentially be unfolded. Now the interesting part is, we will start here with folded proteins, we will then gradually unfold them, and actually here at this peak we have 50-50 folded and unfolded proteins. Eventually we end up with the completely unfolded proteins, but when we now integrate this peak, here we start to unfold the proteins, we see that we have to provide extra heat in order to unfold the protein because we have to break the bonds and things like that. Well, this integral tells us something about the heat of unfolding. We do that at constant pressure. We will learn later that we call that the unfolding enthalpy. Not going to tell you right now why we call it enthalpy. That will be introduced later. But essentially this area under this peak tells us something about the heat required to break the protein structure. This is called the unfolding enthalpy. This is a very important experiment, and I will come back to this a couple of times in this course. What did we learn in this particular lesson? We learned that it is not very easy to describe quantitatively the heat capacity for large molecules, at least not theoretically. And that there is an influence of a potential energy and also of vibrations, and that vibrations, how they behave, depends basically on the frequency and how the energy spacing between allowed energy levels is related to the thermal energy, and this kind of becomes complicated. But what we took away from is that we understood why we could ignore vibrations for small gas molecules, because in that case the energy spacing between allowed vibration levels was very large in comparison to the thermal energy, so that the molecules were essentially stuck in their lowest energy levels for these different types of vibrations, which do not contribute to the heat capacity. This is why we could ignore them previously. That's what we basically learned from this quantum mechanical picture. We learned that we can measure heat capacities also for complicated systems like proteins using differential scanning calorimetry, and what we just saw is that we can use that to measure the heat that is required to unfold a protein using a peak in the temperature-dependent heat capacity that we're measuring while we are changing the temperature.